This problem talks about various motions that a car has as it goes between, say, two trees. And it goes through different stages of its motion, and it wants to know what the distance must be between the trees in order for the car to have undergone this type of motion. So here's what the car does. It starts out here in this first section over here, and for the first 6 seconds of its motion here, it has an acceleration of 4 meters per second squared. For the next 2 seconds, it coasts, maintains constant velocity or constant speed, so a is equal to 0. And then for the final amount of time here, which we don't know what it is, I'll call it delta t3 here. This is region 1, 2, and 3. I'll call it delta t3 here. So for some amount of time that we don't know, it has a deceleration of minus 3 meters per second squared. This is a meter per second squared here also. So the car undergoes this 3 motions. It accelerates for 6 seconds, coasts for 2 seconds, and then stops with this deceleration and stops just before the tree. So the problem wants to know, well, how far must the trees be apart in order for this to happen? So what you do then is you just start plugging into the equations of kinematics that we know, say equations 1, 2, and 3 that we have, to see if we can figure out something about this motion here. Okay? So what I'll just start tracking the position. Say if it reaches this point right here, I'll call the position here x1, and the velocity of the car at that point v1. Likewise over here, I'll call this x2 and v2, and probably this tree over here, we can call it x3, and its speed v3, although we probably won't need the velocity just to answer the question, what is x3, or the distance between the trees. Anyway, so it's fairly straightforward to calculate x1 here. You just fill in equation 1. If we call this initial position 0 right here, it's going to be x0, which is 0, plus v0. The car initially starts at rest, so that's going to be 0. So what we'll have here is just a 1/2 times the 4 times the 6 squared. That's the 1/2 at squared term in equation 1, given that it started at rest with no speed. So there's the x1. The velocity it must have as it accelerates through this region right here at this point is just going to be given by its acceleration times time. V is equal to v naught plus a delta t. But v naught is 0 because the car starts at rest. So the acceleration, once again, is 4 meters per second squared times 6. So it looks like v1 is going to be 24 meters per second. It looks like x1 is going to be 36 divided by 2, which is 18 times 4, which is 132. 132 meters. Okay, there you go. So off you go then. And so what that means now is you start connecting these points together here, and you notice that x1 and v1 are the velocities that the car takes as it enters this coasting zone right here. So what we want to do now is it's not accelerating, so v1 is actually going to be equal to v2. It's going to carry that speed all the way across. So we sort of have that information for us right there. But we do want to know what distance does it cover now as it goes across like that. Well, not too hard to figure out. In particular, we can compute then that x2 then, this position right here, must be x1, because that's where the car's starting as it enters this zone right here. The initial speed it has is the speed it took from its acceleration region, the 24. The 24, and it does this for 2 seconds, as stated by the problem. It coasts like this for 2 seconds, so the 24 times 2. And there's no acceleration, so normally there would be a 1/2 at squared term out here, but it's just 0 because there's no acceleration in this region. So I filled in x equals x0 plus v0 delta t plus 1/2 a delta t squared. So you can sort of compute that a bit here. In particular, x2 is going to be 132 meters plus 48. So x2 then, or this position right here, is going to be 180 meters. That's what x2 is. So by the time the car makes it to this point right here, it's gone 180 meters. Lastly then, the car is going to start to decelerate, so it doesn't hit this tree, and that gives us the last piece of the distance right there. Let's just see what that's going to be then. So a couple of things is we don't know how long it's going to take the car to decelerate. This delta t3 is unknown, but we know it's going to go from speed v2, which is the same as v1, which is 24, to 0. And we can see how long it takes because we know the acceleration is 3 meters per second squared there, the deceleration rather. So we'll see how long is it going to take to stop, given that it started at 24 meters per second minus 3 meters per second squared times delta t. Looks like it's going to take 8 seconds for the car to come to rest in this last region right here. And if we want to know how the distance is going to be now, I think we can do that using the distance form here. Let me just find a spot to write it here. In particular, x3 then, which is the answer we're looking for, the position of that tree. Now x3, the initial position when it started, this section is at x2. That's where it's starting right there. So x3 then is equal to x2, and it does have some initial velocity because it was still, remember, it's moving at 24 meters per second when it enters this region right here. It carries that velocity all the way through, so it has the 24 meters per second that it carries in. So plus 24 meters per second, and we know it's going to be in this region for 8 seconds right there, and minus 1/2 The deceleration is a 3 meters per second squared times the 8 squared, something like that. Now we know what x2 is additionally. That was the 180. Got that from additional calculation there. So x3 then is going to be 180 plus 24 times 8 minus 1/2 times 3 times 64. So you have to crunch some numbers here. But here's one equation that just involves a bunch of numbers here. And it seems like to me you could put this in your calculator here and figure out what x3 is there, and that will be the position of this tree. So by analyzing the motion of what the car had to undergo to stop just before it hit the tree, you are able to calculate what the distance must have been between these two trees. And it comes to just putting this in your calculator.